Hi everyone, I'm Dan Fullerton, and today I'd like to talk to you for a little bit about temperature. Our objectives are going to be to calculate the temperature of an object given its average kinetic energy, to describe the temperature of a system in terms of a distribution of molecular speeds, and finally to describe thermal equilibrium as a probability process where energy is transferred from higher to lower energy particles on average. So, let's start talking about thermal physics. Thermal physics explores the internal energy of objects due to the motion of the atoms and molecules comprising those objects. It also explores the transfer of this energy from object to object. In this transfer of energy, we call heat. Now, to begin with temperature, the internal energy of an object, known as its thermal energy, is related to the kinetic energy of all the individual particles comprising that object. The more kinetic energy the constituent particles have, the greater the object's thermal energy. And for most systems, the kinetic energy of the constituent particles is not the same. You've got a distribution. Therefore, the system is modeled as a distribution of kinetic energies. And typically, we're going to analyze this using what's known as Maxwell-Boltzmann statistics. B-O-L-T-Z-M-A-N-N. Maxwell-Boltzmann statistics. All right, so temperature and phases of matter. In solids, the particles comprising the solid are held together tightly, so their motion is limited to the vibrating back and forth in their given positions. In liquids, however, the particles can move back and forth across each other, but the object itself has no defined shape. And finally, gases, the particles move throughout the volume available. But in all cases, the total thermal energy is the total of the kinetic energies of the constituent particles. Add up the kinetic energies of all the comprising particles, you have the total internal energy. So let's relate average kinetic energy and temperature. Average kinetic energy is 3/2 times a constant, the Boltzmann constant, Kb, times the temperature in kelvins, which is the standard or System International unit of temperature in physics. Now, the actual kinetic energies of the individual particles may vary significantly. Again, remember, it's a distribution. However, the average you get by taking 3/2 times Boltzmann's constant, which is 1.38 times 10 to the minus 23rd joules per Kelvin, times the temperature in kelvins. Now, if you have two objects with the same temperature and therefore the same kinetic energy, that does not necessarily mean they have the same internal energy. Got to be careful of that. So let's start with the sample problem. What is the average kinetic energy of the molecules in a steak at a temperature of 345 kelvins? Well, the average kinetic energy is 3/2 Boltzmann's constant times the temperature in kelvin. So that's going to be 3/2 times Kb, 1.38 times 10 to the minus 23rd joules per Kelvin, times our temperature in kelvins, 345 kelvins. So I would get an average kinetic energy of about 7.14 times 10 to the minus 21 joules. Nice, straightforward use of that formula. How about, given the average kinetic energy of the particles comprising our sun is 1.2 times 10 to the minus 19 joules, find the temperature of the sun in Kelvin? Well, average kinetic energy is 3/2 kBT. And if we want temperature, then we'll rearrange that to say that that's 2 times the average kinetic energy divided by 3 times Boltzmann's constant, which will be 2 times 1.2 times 10 to the minus 19 joules divided by 3 times 1.38 times 10 to the minus 23rd, which is going to give us a temperature of about 5,800 Kelvin. Pretty hot. Let's take a look at some temperature scales. On the left here, we have the Fahrenheit scale. We have absolute zero here at negative 459.7 degrees Fahrenheit. Then we've got a long ways on the scale before we get up to 32 degrees Fahrenheit, where water freezes, and 212 is where water boils. Moving over to the Celsius scale, negative 273.15 degrees Celsius is the minimum, the absolute zero temperature. A break, and then at 0 degrees C, water freezes, and of course, water boils at 100 degrees C. And finally, we get to the Kelvin scale, which is the standard in physics, which is really the Celsius scale, just offset a little bit. Absolute zero is 0 K. Water freezes now at 273.15 K, and it boils at 373.15 K. And just a note here, this absolute zero, that's the point on a volume versus temperature graph for a gas where the extended curve would hypothetically reach zero volume. It's a theoretical minimum. Let's talk about how we convert temperatures from one scale to another. If we want a temperature in Kelvin and we've got it in Celsius, all we have to do is add 273.15 to it. If we want Fahrenheit and we've got Celsius, we take the temperature in Celsius, multiply it by 9/5 and add 32. And if we have Fahrenheit and want Celsius, we take the temperature in Fahrenheit, subtract 32, and then multiply that answer by 5/9 to get our temperature in degrees Celsius. So let's take a look here. Normal canine body temperature is 101.5 degrees Fahrenheit. What is normal canine body temperature in degrees Celsius and in degrees Kelvin? Well, if we want the temperature in degrees Celsius and we're given Fahrenheit, that's going to be 5/9 times our temperature in Fahrenheit minus 32, or 5/9 times 101.5 minus 32 for a normal canine body temperature in Celsius of about 38.6 degrees C. If we want to do this in kelvins, well, the temperature in kelvins is just going to be the temperature in degrees Celsius plus 273.15. So that'll be 38.6 plus 273.15 for a normal canine body temperature in kelvins of about 311.75 kelvins. Hopefully this gets you started with temperature and different temperature scales. If you need more help or are looking for more information, check out aplusphysics.com. Thanks and make it a great day.